Thanks everyone for coming. Thank you for the organizers for putting this together. I'm going to talk to you about something also a little bit broad about the search for tidal disruption events, since this is an observational day. Just starting with one of the fundamental problems that we're dealing with in the search for not only tidal disruption events, but a lot of other transients. And it's that we are used to looking for these things in what we call the stream of transient alerts, right? Digging through a lot of alerts, trying to find these TDEs, when in reality the problem is that it's not a quiet little stream, but we are inundated by an ocean of transients. And it is our job to figure out how do we find the interesting ones, how do we find the tidal disruption events in this sea of transients that we get every single day, right? Ongoing surveys like ZTF and Atlas and PanSTARRS, or even Gaia and TESS, are finding tens of thousands of transients every single year. And only a small fraction of them, the blue little thing here, are the ones that are spectroscopically classified. Spectra has always been the gold standard to classify a transient, but we only have spectroscopic resources in the world to classify around 10% of all of the photometrically discovered transients. And it is in this little blue corner right there where we find effectively all of the TDEs that we know about. And the problem is that TDEs represent only around 0.5% of all transients discovered by these surveys, right? So if you want to find more TDEs, doing an unbiased survey, doing a systematic survey, is not going to be an efficient way of finding more TDEs, right? And this is going to be an even bigger problem in the coming future when the Rubin's survey, Legacy Survey of Space and Time, or LSST, begins next year, and it's going to increase the transient discovery rate by about 2 orders of magnitude, making our job even harder. So it's not going to be, oh, we have resources to classify 10% of them. It's going to be 0.1% of them. So if you have 1,000 transients in a year, which one do you pick to follow up, right? That's the kind of numbers we're working with. And then the year after, the Nancy Grace Roman Space Telescope is going to launch and explore a whole new region of parameter space. If you're not familiar with it, oh, I am missing a slide. Anyway, if you're not familiar with it, Roman is a telescope launching in late 2026, no later than 2027, that is going to have 100 times the field of view of HST. The HST field of view is right there. This is Roman. All data is going to be public immediately. It's an infrared telescope. And for context, I was just having this chat during lunch. That is the entire, so the archive that Hubble generates per day, 3 gigabytes. JWST generates 60 gigabytes per day. Roman is going to generate around 1.3 terabytes of data a day, right? Just for context, the HST's entire archive is 172 terabytes, and Roman's current data set, it hasn't even launched, just dark frames from a vacuum chamber, already 600 terabytes. So it's going to be an insane data generating machine that we need to be ready for, right? And that is why we need algorithms like FLEET, which is a code that I wrote called Finding Luminous and Exotic Extragalactic Transients. And this is a machine learning algorithm that can take in any transient that has been reported to the transient name server. It uses catalogs, public catalogs like STScI and PanSTARRS and Gaia to associate it with its most likely host galaxy. And then we can start deriving properties of the galaxy for each specific transient. What's the separation to the galaxy? What is the color of that galaxy, etc. Then it fits a very simple model to the light curve of the transient. These are being gathered from ZTF. We used to use all other surveys, but we realized that most of them just come from ZTF. So now we are focused just on ZTF. And then it uses machine learning algorithms to try and predict what kind of transient this is. And it's publicly available on GitHub. Anyone can go in and use it. This was the first code that was able to do this for TDEs. Now there's a second one, TDE score. But given that there are so few TDEs, this has not been possible until recently. And just to describe a little bit about how the code works, it is based on decision tree algorithms. And decision tree algorithms are a machine learning framework by which you ask what set of questions can I ask to better separate objects into the purest classes they can be. So to explain this with goats and cows. So if you just have a bunch of goats and cows and you want to ask questions about what questions can I ask to separate them best? Like, are they white? Well, both cows and goats can be white, so not great, but maybe. Are they small? Most cows are big, so yeah, that works, but some, what about a baby cow? So a decision tree algorithm will fit the best set of questions to separate these into groups. And that's what we're doing, but with tidal disruption events and other types of transients, to really have a sense of what questions to ask to separate these. So when you get a new object, if it falls in this, like in this case, group number 2, we can be n% certain that it is a tidal disruption event. Based on all of the features that we've extracted from the code and all of the public catalogs, we determined that these are the most important features to look for when finding a tidal disruption event. The color of the transient, the duration of the light curve, they are generally pretty long-lasting. The color of the host, how far away it is from the host, that one's pretty obvious since effectively all TDEs that we know about are nuclear, and the time they take to rise. Like I said, the sample of TDEs right now is relatively small, so this is trained on 46 TDEs and a few thousands of other types of transients. And we find things that, like, well, there are all the yellow ones, they are blue, GR color is pretty blue, and they're nuclear. This is the normalized host separation, right? These are the kinds of plots that Fleet generates as diagnosis, because we are not at the point where we can use these machine learning algorithms completely blindly, right? We still need some human vetting. So we run this on thousands of transients, then Fleet returns, okay, here are the 10 most likely ones. Just look at them and verify them before triggering a telescope. So we can see things like the separation to the host galaxy, make sure that the association is correct, get a little light curve with a fit, is it observable, are there any information about the redshift, what is the probability that the closest object is actually a galaxy and not a star, things like that, right? So this can really help us decide how to best use our limited resources and our limited telescope time. How do we use that 10% of spectroscopic time that I talked about at the beginning to trigger on the most interesting things? And I think in this audience we would agree that TDEs are pretty interesting. So these are the predictions of what we can do with Fleet. This is a plot of completeness as a function of probability of being a TDE. What this is saying is that if I observe everything with a probability of being a TDE greater than, say, 10%, which is effectively everything, then I'm going to get effectively all TDEs, right? But at the expense of contamination, because the purity or the number of actual TDEs that you will get is pretty low, right? Usually the threshold that we work with is a probability of being a TDE greater than 50%. So in that case, the completeness we expect is around 45%, and the purity that we expect is around 35-ish%. What that translates to in the real world is that if we find around 1,500 transients a month, just ZTF and these surveys, that's around 1 or 2 TDEs a month that we could find, which is already 100 times better than the random selection that you would get from that 0.5% of the normal rate of TDEs. And actually, we have already done this for superluminous supernovae. Fleet was originally written for superluminous supernovae, which are observationally kind of similar to TDEs. They're blue, they're bright, and they're long-lasting. These were our predictions a few years ago. Completeness around 30% and purity of around 56%. We ran this survey for 2 years, and we surpassed both our predictions. Our real world purity was 80%, and the upper limit on the completeness around 50%. So we've proven that Fleet actually worked, and we ran the survey, and we found a lot more superluminous supernovae. So now we want to do the same for TDEs. And this is just the beginning. We are starting the survey. I don't have the results for that yet, but those will hopefully be coming soon. And one of the questions is like, okay, so now we have this algorithm that can help us find more of these TDEs, right? What can we actually do with these objects that we found? And the first one that was actually mentioned several times during this talk is diversity. I think we've learned that there's a lot of diversity from TDEs that we don't yet understand, right? Some of them have helium lines, some of them have Balmer lines, some Balmer-Bowen, some of them show radio afterglows, some of them have X-ray polarization, some of them don't, some of them have narrow lines, broad lines. There's a lot of diversity in this object, in these objects, so we really could use a bigger sample size because we only have around sort of 50-ish well-characterized TDEs that we know about. So finding more of them can really help elucidate the question of what does the general population look like, right? And another thing that I find very interesting that we can do with TDEs is measure the masses of the supermassive black holes that disrupt these TDEs, which has been done previously by measuring, by fitting the light curve of the TDE. You can get an estimate of the black hole mass and then compare that to, say, an M-sigma relation. And this is particularly helpful at the low mass end. So this is a plot of the M-sigma relation, right? And you can see that below black holes of 10 to the 5 solar masses, it's pretty empty. We don't know if the M-sigma relation actually continues that way. And if I plot it as a function of galaxy mass, you can see that smaller galaxies are expected to have smaller black holes, which makes sense. This is a sample of some of the smallest black holes known. So what's going on here is that is where you might be able to find these low mass black holes, or sorry, intermediate mass black holes in dwarf galaxies. And TDEs might be a way to find these objects. The problem is that the only stars that can get disrupted by a black hole less than 10 to the 5 solar masses are white dwarfs. And all of the TDEs that we know about, or at least effectively all of them, come from regular main sequence stars, right, which can be disrupted by black holes between 10 to the 5.5 to 8 solar masses. But anything lower than that, and only a white dwarf can get disrupted by an intermediate mass black hole. And this can be observed as a white dwarf TDE, right? So if a white dwarf comes near a supermassive black hole, due to compression of the white dwarf, you're going to see this detonation of the white dwarf, which is going to look like a type 1a supernova, because it's still a white dwarf exploding, but it's going to be dimmer, because you don't need to have this Chandrasekhar limit of 1.4 solar masses. It can be a white dwarf of any mass. So they are expected to be dimmer and to have the silicon-2 line at an opposite velocity due to the motion of the white dwarf. So we can look for these 1A TDEs in optical time domain surveys like CTF to try and see if we can find these intermediate mass black holes. So if you find a 1A TDE, that means the thing that disrupted it was an intermediate mass black hole, which means we can use it to constrain M-sigma relations and learn more about the population of low mass black holes. So we did this. We did a preliminary experiment in which we went through the entire ZTF archive, all light curves, right, to try and find, are there any transients that are consistent with the white dwarf TDE models? And we found 4 that are reasonable candidates that are spectroscopically classified, and 2 that are reasonable candidates that are spectroscopically still unclassified. So around 6 of them. This is the plot of the 4 classified ones. None of them are perfect. Some of them are slightly off nuclear, which is not necessarily a killer, but it's not a good indication. The spectra, some of them match pretty well. Some of them have features that don't quite match. The light curve evolution tends to agree generally well. So this is not by any means a done deal, but it's an indication that yes, we have the infrastructure that we need to start looking for these white dwarf TDEs and see if we can find intermediate mass black holes by observing more of these TDEs. We can also measure the galaxy masses from existing catalog photometry and go back to this plot that I showed at the beginning, where you have all of the low mass black holes known, and we can plot them there, right? We don't have an estimate of the mass of the black hole because these are old transients that only had ZTF GNR photometry. We don't have enough information to do it. But if we can find one of these in real time, that will really help us constrain this M-sigma relation and look for more of them. And maybe the way to do this is by waiting until LSST gives us 100 times more sample size and really make this process a lot more efficient and hopefully be able to find some of them in LSST. To predict roughly how many TDEs we can find in LSST, we injected 30,000 simulated light curves of real TDEs. So like drawn from samples of real observational TDEs. They're not TDE models, but samples of real TDEs into LSST. And here's a histogram of what we expect to find from LSST. This little green histogram is showing you the well-observed TDEs, meaning they have 20 data points over 70 days. Most of them will peak around redshift of 0.5 to 1. Assuming Short's TDE rate, that's around 10,000 TDEs a year that we could find from LSST. And we did the same thing for Roman. Roman will find a lot less, around 200 TDEs per year. That's our expectation. But if they exist, they can be detected up to a redshift of 5, 6 or more, right? If they exist, if they are the same as in the local universe, the survey is deep enough that we would be able to do this. And just to mention this, the Roman survey right now is planned on 16 square degrees in the sky, a 5-day cadence in 6 filters, but these numbers are not set in stone. We want your input. This is just the nominal first suggestion of a survey design, but right now we are in the process of defining the future of the high latitude time domain survey, which will be the future of high redshift transients and infrared transients. So if you have input on what you think should matter when designing the survey, please talk to me, and we will take that into consideration when deciding the parameters of that survey. For example, one thing that I really want to do is to extend that survey from 2 years to 4 years at a very low cadence, because like TDEs are very slow. So if we do observations every 1 month, every 2 months, we can find these super high redshift or super slow events. In this case, PTF for them and 14 HLS, and this will be helpful for all long duration transients like TDEs, superluminous supernovae, parent-steadily supernovae, etc. Before I conclude, I'm just going to give try to sell the Transient Sky Alliance, which is a Slack space that we have built for all things transient. I know a lot of people are using it to advertise their conferences, their jobs, maybe some transient-related thing you want to advertise, but also it's very helpful for collaborations. There's a lot of private spaces. It's organized by Space Telescope, so it's paid. Messages will be there forever. If you're interested in joining, let me know and I'll send you an invite. But with that, I will leave it open for questions. Thank you.
Okay, open the floor for questions.
I may have missed this. For the 1A TDE, if the transient is powered by the nuclear burning in the white dwarf, what allows you to... Sorry. Yeah, for the 1A TDEs, if it's the nuclear burning of the white dwarf that powers the transient, what's allowing you to get the black hole mass?
Oh, Sarah?
Maybe I could just use it. Sorry. For the 1A TDEs, if it's nuclear burning in the white dwarf that's powering the transient, how are you getting a black hole, or how do you expect to get a black hole mass estimate?
Yeah, so the one expectation is that there will be X-rays from the 1A, which like normal 1As don't show X-rays. So if we find X-rays, that's probably an indication that we're looking at something that's consistent with this. And assuming Eddington limit, that correlates with the black hole mass.
But for TDEs, we're seeing potentially a wide range of Eddington ratios. So how well do you think you can actually constrain the black hole mass?
That's we're going to have to work with theorists because, again, yeah, there's a wide scatter, and we don't have a lot of samples for these. Yeah.
I was also going to ask you about the black hole mass.
Yeah.
Is there is it mostly just a matter of getting simulations that predict enough observational features? Should there be something in the spectra eventually that we would see?
Yes. So for the spectrum, well, it's dimmer, right? That's one thing, and also the silicon line should be should have a high velocity because of the motion of the white dwarf around the black hole.
Yeah, and will that offset give us enough information to kind of constrain that, or is that just mostly for classifying this from another kind of
Right now we're using it for classifying, but that's an interesting point. Like if the black hole mass correlates with the expected velocity of the white dwarf, I guess we could use that. Yeah.
I have a question about fleet.
Yeah.
So the statistics you showed, this is assuming you have the whole light curve, or can you? How well does the classification do if you want to catch it on the rise, for
Yes.
example?
So these numbers are for post-peak, which is a past 40-ish days after explosion. Well, after first detection. 40 days after first detection, fleet's ability to classify the transient kind of flattens out because it's dominated just by the presence of the peak. If we only use the first 20 days, predictions are around half the purity, but we haven't had a lot of success with that yet. It seems that we really need a peak.
Okay, thanks.
And my question is also on the white dwarf, IMBH. So suppose that you can find them in real time. The best way to measure their black hole mass, you think, is to get the X-ray luminosity and scale it with some Eddington ratio?
Yeah, that's one option, yeah.
Okay. And for your ZTF candidates, do you have any X-ray constraints?
No, there's nothing else.
Okay, fine. Yeah, I was intrigued by the white dwarf thing. So a couple of questions regarding that. Firstly, do you know if there's any estimates for rates of such white dwarf TDEs? And second, like how a TDE in a white dwarf can trigger a 1A explosion? Can this happen in stars? Not at 1A explosion, but like can it trigger fusion of in the core of heavier elements?
Yeah. For rates, they're very rough because they come from theoretical expectations of what you might expect the white dwarf population in the center of black holes to be, galaxies to be. I seem to remember it was a few % of the normal rate of TDEs. And for the stars question, I think that's a question for theorists. I don't know.
Okay.
Yeah.
Hi, so I have a question about the general strategy of searching for transients with Roman. As you have shown, like the redshift of detection can go to like 5, 6, 7, right?
Yeah.
So the light curves are going to be stretched. So the transients may not look so transient anymore.
Yeah.
So how are you going to modify the criteria to still be able to find these transients?
Yeah. So that is part of the reason why we are motivating this like long duration strategy where you have this very low cadence, or you can have a whole new set of data processing pipeline that binds data. Because like you said, like if you are taking data every 3 days and only compared to the previous day, you're not going to notice these changes. But if you average everything in epochs of like months or years, right, you're really going to start to be able to recover these super slow duration transients that are really the high redshift transients that we couldn't find otherwise. So it requires, the main limitation for that is computational power, because stacking takes a lot of computational power, and especially if you want to do it with a variable bin size, like in only bin 1 month or 1 year, it involves reprocessing the entire pipeline, whether that's ZTF or Roman. So it's mostly a computational limitation right now. But yeah.
Thanks.
If you select your Tidal disruption events very efficiently, but we have this large diversity and the many types we don't know yet, do you not exclude the new things, optimizing, repeating what we know?
Yes.
This is my first question. And my second one, your motivation is the observing time. The observing time is more or less stable. If you go to sources factor 10, 100, lower influx, you need a factor 10 and 100 more observing time for one source.
Yeah. So for the first question, yes. By the fundamental limitation of machine learning is that we're only going to find things that look like the things we already know about. So we are not really sensitive to really different TDEs. But we did run the analysis to ask, does Fleet introduce any additional biases than you would find from just using selection cuts? By comparing the Fleet selected TDEs with all the other TDEs, and we find variations in physical and observational parameters of 5-ish%. So at least it's not introducing additional biases, but yes, that is one of the big limitations. And then the second question about the flux.
Or that you will need a lot more observing time if you go deeper for follow-up.
Yes.
Great talk. So when obviously you're looking for these white dwarf TDEs, not just as like unique one-off events. Have you thought about different criteria you might use to look for just like regular star, because you would get star disruptions, just more of them, they'd maybe be less relativistic, less bright. But have you thought about how you might look for those in your current sample, or are those sorts of searches? I remember, and I've seen this list before of how the TDEs are generally picked out from like CTF, but I could see like TDEs around IMBHs just of normal stars failing a lot of those criteria.
It's quite straightforward if we have the criteria from either models or expectations to build that into Fleet or any other pipeline. Right now I'm using Morgan McLeod's models and just say, these are the expectations, just put that into the Fleet database and output the most likely TDEs. So if you have expectations for what you think this disruptions might look like or what location in the galaxy they might be, we have all that information. So it's relatively straightforward to make the cuts.
Cool, but you haven't at this point looked?
No, I haven't.
Okay, cool.
Yeah.
We should talk, yeah.
Thanks for the talk. So this morning we heard a lot about how like radio and X-ray emission from TDEs doesn't always doesn't occur on the same timescales as optical, right? And so does Fleet tell us anything about if we should be following these up in the radio? Can we follow them up in the radio? Is there likely to be radio emission?
So Fleet, Fleet is completely agnostic to that because it's just using the entire database of TDEs to say like this is likely to be a TDE or not, but it doesn't actually provide any information about the type of TDE. At that point, you can do things like model the light curves and see how they correlate to parameters, but that's completely independent of Fleet.
So I also have a question about the white dwarf TDEs. So I guess for helium white dwarfs and CO white dwarfs, like the nickel 56 yield and like the appearance will be quite different for those two. So does your selection criteria capture both of them?
No, it does not, because right now we're basing it on models that are just like 50% carbon oxygen white dwarf. So if it's a different model, we would need to rerun those simulations and try again. Yeah.
It gets taller every time. Can you just recap for us what we should? Thank you. What we should look for these 1A TDEs? You said kind of dimmer, silicon lines.
So yeah, it's dimmer, it's silicon lines, X-rays, and the expectation, and depending on the angle of the jet, if there is a jet, possible radio detections within like a month after disruption.
So do you have a good idea of what is more important, sampling in the light curves or color information, or because Ruben will not give us great light curves?
Yeah.
Just to get like, do you have a feeling for how much worse or better it might get your photometric classification?
Yeah. Very preliminary, but U band and especially like the bluer bands, I think are really critical to distinguish TDEs from other transients. But I have not run the full analysis. And cadence is actually not that critical because they're pretty slow. So that's probably fine.
Okay, if there are no more questions, let's thank Sebastian again.